In the previous video, we converted from binary to decimal, and the objective for this video is to convert from decimal to binary. So again, quick recap of what we've done before. So we went from binary to decimal, and this video will focus on decimal to binary. Okay? A quick overview of how we did this. I've mentioned it's always a good idea to at least know some binary equivalent values in decimal, mainly up to 8 bits. So let's go ahead and do something like that. So 2 to the 0 will be the first position. So 2 to the 1, 2 to the 2. So notice I have the base, and 0 is the value of the position or the column we're on. 2 to the 3rd, 2 to the 4th, 2 to the 5th, 2 to the 6th, 2 to the 7th. Now again, as I mentioned later on in computer networking, this conversion here will come in really handy. So 2 to the 0, anything raised to the power of 0 will be a 1. So this would be a 2. This would be a 4. This would be an 8. This would be a 16. This would be a 32. This would be a 64. And this will be a 128. So let's just keep that in mind in case we want to know how to represent anything within this range. So for example, if I get something like this, 1 0 0 0, right, as a binary number, okay, it's going to fit this pattern. This is position 0, this is position 1, this is position 2, and this particular one is position 3. So that tells me this whole thing, right, since the 1 is in position 3, 0 multiplied by any of these weights will be 0, then this will be equal to 8 in decimal. Okay, so this binary number is equivalent to 8 in decimal. So if I have another combination, like let's say 1 0 1 0, then I have two places that have 1s in the 1s column and the 3 columns. So that's an 8, and this is a 2, right? Since the 2 is right here, you add this up, and this will be a 10 decimal. So anyway, this was a quick overview on how to convert, again, from binary to decimal. Okay? Now we're concerned about decimal to binary. So that means, let's suppose I have that 10 that you just saw here, and I want to convert it to binary, right? So let's say I have 10 in decimal, and I want to convert it to binary. Now I've used a quick trick, is I divide the decimal number that I have by 2, and then I keep dividing until my last result, okay, is either 0 or 1. Okay? Aha! So we're going to divide this by 2. And notice what I'm going to do now. Okay, so it's going to be a little wonky here as far as my division here. It's going to look more like a European division. Okay? So 10 divided by 2 gives me a 5. Now if you multiply 5 by 2, that's 10. 10 minus 10 gives you a 0. So my remainder is 0. The result is 5. So keep the remainder here and keep the result right here. Then you're going to take this result and divide it by 2 as well. And you're going to say, okay, well, what is 5 divided by 2? Well, at least I know, and you need to be an integer whole number, right? So at least there are 2 in there, and the remainder is 1. Is it true? So if you add 2 times 2 is 4, plus 1 is 5. 5 minus 5 is 0. So that works out nicely. So again, this is a remainder. This is a result. Okay? So I'm going to divide this by 2. What is 2 divided by 2? Well, at least there is 1 of it. And you stop here in terms of dividing. But you need to take care of the remainder. 1 times 2 is 2. 2 minus 2 is 0. Aha! So now what you do is the last result that you would have here, you're going to call this one the most significant digit or the most significant bit since it's in binary. Okay, so we'd like to use the MSB instead of MSD. Most significant bit. Okay, so if that's the most significant bit, we're going to read backwards. We're going to read this result, including all of these remainders, where the last remainder, and if we want to express it in bit, will be the least significant bit. So again, LSB stands for least significant bit. So if you're going to have to write it, you always start with the MSB as the leftmost digit. So that would be the one that's carried over from here. And that would be the 0 that's coming in from here. And this would be the 1 coming in from here. Remember, I'm reading in the sense of this arrow. And lastly, the 0, which was the LSB, right? The least significant bit. So what do I end up with as a pattern? And remember, this is binary. So base 2 or D, B or 2. 1, 0, 1, 0, which takes us back to this value that we had here. So that's overall the method, my choice on how to do this. Now, you have calculators that will do these conversions automatically, okay? But in case you have a piece of paper and a pen and you have no choice but to convert manually, this is a quick way to do it. So let's do our larger number. Let's do 53. Okay? So 53. So what, and it's in decimal, base 10. We want to convert this to its binary equivalent. Okay? So we want to convert it to its binary equivalent. So what do? We take our 53, again, divided by 2. Now, if you're not sure, you could pull your calculator, okay? Here, let me just do that and show you. And you take 53 divided by 2, that gives you 26.5. You stop. Do not use 26.5, just use 26. So the nearest number, rounded up to the nearest number, lower nearest number. So you're going to say 26. Now, great. So what's your remainder? So if you take your 26 times 2, that's 52. So your remainder will always be either 1 or 0. Now, obviously, this is going to be a 1 since 53 is an odd number, right? Cool. So now I have 26. You're going to take 26 and divide it by 2, right? So you take 26, again, divided by 2. Okay, and oops, my calculator is wrong. I know where the result is, divided by 2. Okay, it's 13. Now you can do this in your head. I just want to make sure that I don't do any oopsies in here. All right, so 13. Now remember, this one is even. There are 2 13s in 26, so the remainder is 0. You're going to take 13 and divide it by 2. And again, you're going to take 6 here, since 6 times 2 is 12, and the remainder is 1. You're going to take this 1 divided by 2. You know there are 3 in there. 3 times 2 is 6, remainder 0. You're going to take 3 divided by 2. You know there is at least 1, 2, and 3. But you're going to have a remainder of 1 since 3 is an odd number. Again, this will be your MSB, and you're going to read backwards like this until you reach the LSB. So MSB being the most significant bit, LSB being the least significant bit. So let's write it up in here. 1, 1, 0, 1, 0, 1. Again, the most significant bit on the left. The least significant bit will be on the right. Now, can we prove backwards that our result is correct? Well, to do that, then we'll have to do a binary to decimal conversion, right? So we're going a full circle here just to prove the point. Okay, now remember this list that I have here. This could come in handy. So we know this is 1, this is 2, this is 4, right? So the weights, this is 8, this is 16, and this is 32. So anytime you have a 1, those are the ones you're going to add up. So we're going to convert back to decimal, and we're going to add up 32 plus 16 plus 4 plus 1, right? So if you add all this up, what do you end up with? 53 in decimal. So I hope this little tour here gave you an idea how to convert from decimal to binary. We're going to see again in the next video another numbering system called the hexadecimal numbering system. And another video again, we're going to see how to do octal or any other base. Okay, so they don't have to be just hexadecimal base 16, octal base 8. Right? In some systems you may have, or some, especially in mathematics, you might have different kinds of bases with which you do calculations. But for us in computer science and engineering, electronics engineering, we're mostly concerned with binary, hex, octal, because they're a much easier, higher level representation of the data type that we deal with, and or the state of the hardware we deal with, since most of the hardware we deal with are switching based off either on or off kind of status. So it's really a binary state. We're just converting these binary states into a higher level number so we can give it values, okay? How do we store something in memory, right? So we could write it in binary, or we can write it at a higher level in decimal, something that most mere mortals will understand. And you could say, okay, I stored 15 in memory. But really, is it 15 as we know it? No, it's going to be a 15 in binary. But is it really a 15 of ones and zeros? Not really. It's in the memory chip. Depending on what technology is being used, if it's a bunch of charges, either a cell is charged and the other one is discharged. If it's magnetic, either one is north, the other one is south. So whatever that ones and zero represent physically is what really truly happens at the physical layer or level of the hardware. But in our case, we like to bring things up to something we can analyze and process. This is why we need to understand conversions. Okay, so I hope to see you again in the next video dealing with hexadecimal conversion from hex to binary, binary to hex, hex to decimal, and decimal to hex, okay? So some of these concepts and these calculations we've done, we're going to see them again. So I will see you again for the next video. Thank you.